Hi, my name is Evan. I teach 7-8 math at Synapse. I'm a 7th grade advisor. 7-8 math is all about, well, it's about lots of things, but at its heart, it's about the beauty of mathematics, the weirdness of mathematics. It's also the first year that kids really get to grapple with like algebraic manipulation and symbolic mathematics. We look at kind of tying all those pieces together to both sort of put a cap on their Synapse experience and also help prep them for a rigorous high school mathematics program. Some of the things we do, we have a project where it's a geometry project where we have the kids build and literally 3D print weird geometric dice in irregular shapes. So they get to calculate like, what is the probability of landing on like this strange trapezoid? Like, what is the ratio of the surface area? How does this work? Or what is the odds of landing on Jake the dog's nose? All of these are dice that have been made by children. They design them in CAD software. We 3D print them on our class 3D printer. They roll them, they test them, and then they have to ultimately justify why experimental and theoretical probability are different. Why, if you think something's going to happen and the math says it should happen, like Jake the dog should always land on his round side, why does he sometimes land head down? Like, experimental and theoretical probability diverge, and we talk about why that exists. Some of our other projects we do that I'm like particularly proud of, we do the geodesic dome. So we start with like triangles and basic geometry, and we look at the platonic solids. This is a platonic solid, this is a dodecagon, for example. And then we look from there at these. This is a soccer ball. How is this soccer ball different than this? It's like, well, it's got hexagons on it, and it forms a sphere. The angles don't work. We look at angle theorems and why this doesn't work. Then we break it down. This is actually a kid made this. How does it construct into triangles? What are the angles? What's the geometric properties? And then in the end, the final project is take them out with a bunch of power tools, and we built that thing, which is maybe my favorite single giant object at Synapse. We built a 20-foot geodesic dome, and that is fundamentally just a soccer ball. And all the kids can explain like why the geometry checks out, why the shapes work, why everything kind of makes sense mathematically in that strange object, in spite of it not necessarily being immediately obvious when you look at it. And so all of that is designed to build kind of a sense of wonder and a sense of curiosity about mathematics. It's also designed to get them really thinking about solving problems in a way that is not necessarily linear or straightforward or out of the box. Understanding formulas is important, and they certainly look at things like what is the area, how do you calculate the area of a regular hexagon, and like those kind of core 7th and 8th grade content skills, but we also look at taking that and making that more abstract and looking at like how do the rules of geometry break when you do them on a sphere. Another one of our projects that we do is we look at cooking, and we cook breakfast, and so we think about like, okay, if I'm cooking, say I'm cooking pancakes, I'm making enough pancakes for 2 people. We have the kids decide how many pancakes is enough pancakes for 2 people. Like, oh, well, I eat 2 pancakes and he eats 2 pancakes, so we'll do 4 pancakes. So 2 people need 4 pancakes. We have them get a griddle out and they cook 4 pancakes and they time it. And they're like, okay, so pancakes for 2 people takes, I don't know, 135 seconds, and that's a data point. And then they're like, okay, well then if I cook pancakes, then we have them do a big one. Right? So say I'm cooking pancakes for 20 people. How many pancakes? 40 pancakes. Okay, well pancakes for 20 people. It's all the way out here, and that took them like, I don't know, like 397 seconds, whatever. And what we get in this situation is you have a line, right? So that's pretty solid so far. And then we're like, okay, what about scrambling eggs? When I scramble eggs for 2 people, it takes me 180 seconds. But I'm scrambling eggs for 20 people, it only takes me 250 seconds. And we have them making these food in class, which is hilarious, because kids love to cook and they love to eat and everything better. And then you see like, oh, okay. At some point, it becomes more efficient to cook eggs than pancakes. When is that? How do you know it? So it's a classic linear algebra, like, you know, Bob's on a train leaving Dallas at 2:45 p.m., traveling at 70 miles an hour, and Debbie's on a train leaving Austin, right? It's that classic boring algebra problem, but it becomes real, it becomes physical, and the numbers are numbers they've generated by timing their friends, cooking food, and then at the end they get to eat pancakes, and everyone loves pancakes. And they have to like the rigorous mathematical modeling, and it doesn't have a friendly answer. Like it might not be, I just made these numbers up, but it might be that like at 57.3 people, you're more efficient scrambling eggs. And then you're looking like, oh, okay, in what situation would I need to do that? Where do these break down? You're solving really complex systems of linear equations in a way that is authentic, in a way that is self-motivated in a way that is delicious. And that's really what we try to do. We try to make math authentic and delicious, as well as making it mathematically rigorous and powerful. And that's 7-8 Math.